Hi everyone. Welcome to this hands-on session about how to use the KORTEX API for high-level movement. Today we will continue building the class KORTEX robot that we started building in the previous hands-on video, and we will implement a more complex script. So just last time, let's begin by taking a look at our header and seeing what we will implement today. First, as you can see here, I made a new struct named Cartesian vector containing floats for x, y, and z. This will be a convenient struct to carry around in order to be able to send Cartesian coordinates to our robot. This function contains mostly convenient methods like operator plus, norm, and normalized values. Now, if we move back to our main class, the KORTEX robot, you will see that I have modified the initialized function mainly to be able to add a new client. I added a disconnect function that will allow us to disconnect cleanly from the entire server and unallocate the memory even if we do not destroy the KORTEX robot object. And I also added an isConnected getter to tell us whether or not the robot is connected. Finally, our main deal today will be to look at this here, all related to high-level movement. So if you remember in our last video, we took a look at all the methods that we would be able to use for high-level movement. So mainly we learned that we could execute existing actions, move to Cartesian poses defined by Cartesian positions and orientations, move the robot to a desired set of join angles, and we could also move the robot using velocity commands either in Cartesian using twist commands or using join speed commands. Additionally, we also learned that you can change the reference frame for twist commands using a new reference frame. So this method here will allow us to switch from one reference frame to another. After that, we also used all these functions to create sequences, play sequences, execute actions. And additionally, in order to use all this properly in a program, we will need additional functions, namely wait while the robot is moving, as well as a stop function. Finally, as promised in the last video, we will also complete our onAction notification callback. Now in terms of attributes, I've also added an integer naming the number of degrees of freedom of our robot. This is important because we will send join commands to our robot, and if we have a 7 degree of freedom robot, we cannot send only 6 commands, or we cannot send additional commands that do not belong to any actuators. I'm also adding this boolean named isBusy that will tell us whether or not the robot is available to receive an action. I'm adding an internal action that we will modify in order to send all the actions that we will define in our methods here. And finally, I am adding this pointer to a control config client. This control config client contains all the information about how the robot behaves in the various control modes. So specifically here, we will use it to change the reference frame for the twist commands. Okay, so now we're ready for implementation. As you can guess by looking at the number of methods we have here, there's a lot of implementation ahead of us. In order to avoid the video to last over an hour, as you can see here, I've already coded the entire skeleton of our implementation and only kept the detail of each implementation to do today. Let me know in the comment if you prefer this format over the original format where I was writing down every single line with you. So now let's begin by taking a look at our new constructor. Initially, we were only taking in the IP address and waiting to be initialized. But now we also have to tell the robot whether it's connected and whether it's busy. So first, when we create our object, we're not connected to the robot, so it's impossible for it to actually already be connected or busy. Then I'm calling the initialization function. This will allow us to clean our main script and get rid of this line to initialize the robot manually. As soon as we will create our robot object, it will be initialized and connected. In our Destructor, we want to disconnect the robot, and this disconnect function, as you can see, is basically the same implementation as our original Destructor, except it's much safer regarding memory allocation. So first, we're taking a look whether or not the robot is connected, because originally it now connects automatically. If it's connected, we're closing the session, deactivating the router, and disconnecting the TCP client. And then we're destroying all the memory allocated for all the different clients. The main body of our initialization function hasn't evolved much. Right now, what's new is we're checking if the robot is already connected. This way, if you call the initialization function many times in a row, we first disconnect and avoid memory leaks. Then I'm also adding this control config client, which, as I said before, will allow us to change the reference frame for our twist commands. And finally, I'm filling in the number of degree of freedom of our robot by calling the base client getActuatorCount.count. This way we will be able to know how many commands we need to send when we're sending joint commands. The next few methods we already implemented. Subscribe to notifications here is unmodified, as are unsubscribe to notifications, as well as on error. However, our on-action notification callback can finally be implemented. So we know we've subscribed to action notifications, but what do they contain? If we take a look at the documentation that's available on the Kinova GitHub repository, we can learn that actions notifications contain action events, and those action events are enums that can take the following values. There are three main types of action events. The first are execution, the second are pre-processing events, and the last one are post-processing events. Because what's actually interesting to us is whether or not the robot is started or is done moving, we will mostly be interested in the action events, so values 1 through 4. Let's see at how I implemented this. So we receive our notification and take a look at its action event. We can compare it with all the values that we're interested in, namely action start, action end, abort, and pause. So whenever the robot sends us the action start notification, we know that the robot is busy because it's going to accomplish an action. And then I'm adding this message here just to let us know that the action has started. Then for every other case, the robot is actually stopped moving, either because it's done or because something happened, either an error or a manual pause. So in all those cases, the robot is not busy anymore. And that's it. That's all we need to know about notifications. Okay, so we're finally ready to move on to our actual high-level movement methods. First thing we learned to do last time was to execute existing actions. To execute an existing action, we need its name as well as an action type, because we're going to look through the robot database for all the actions of this action type to find the one with the name we're looking for. But before we do any of this, first we need to check if the robot is connected. If the robot is not connected, not only won't we be able to send commands, but we would be also trying to call methods from pointers that do not point to anywhere. Additionally, we need to check whether or not the robot is busy, because if the robot is already performing an action, then we wouldn't be able to send another action. In either case, if the robot is not available to process our action, we return false. Otherwise, we're ready to try and find and execute our desired action. Now let's peek at how we did last time. So last time, what we did, we used the base to read all the actions from a certain action type in the database, and then we looped through all of them, compared their name to the name we were asking for. Last time it was home, and then we recorded the handle. So let's do exactly this. Now let's modify a few things considering we're now in our class. This is an action type named like this. And instead of specifically looking for home, we'll look for the action name we're specifying as a parameter. So now we can hope that we've found the action we're looking for, but what if we haven't found it? If we haven't found it, then our action handle will still be set to 0. So if handle, if its identifier is still 0, then we haven't found anything and we need to return false. Let me fix this here. That was a copy pasting error from earlier. And otherwise, then we have found the function we're looking for and we're happy. So we can call the base client and use execute action from reference from our action handle. So now we checked whether or not we were able to communicate with the robot. We found our action, we send it to the robot. Hopefully there was no error. But then, if we were to proceed immediately with our next function, it would be possible that we arrived to another execute action before we were made aware that the robot is busy. So it's possible that there's a small delay between the moment where we launch our execute action and when we receive the notification telling us that the action has started and where we know that the robot is busy. In order to avoid this, we are adding this sleep function here for 500 milliseconds. Now let's proceed with the move-to method. The move-to method contains as parameters a T-Cartesian vector defining the position as well as another one containing the orientation in the Euler X, Y, and Z standard. We also take Cartesian trajectory constraint in order to be able to constrain our motion, for example, by defining a duration or a velocity during our motion. The same way we did when we were looking for an existing action, we want to return false if the robot is already busy or if the robot is not connected. Then we need to define a reach pose action. So our reach pose action, we will take our internal action, take its mutable handle, and set its action type to a Kinova API base reach pose. So now our action knows that it's going to be a reach pose. There's a missing capital A here. So now that we have a reach pose, we need to define the pose that we're interested in. So we want our action, then get its mutable reach pose, and get its mutable target pose. The mutable target pose contains both the position and orientation separated in all the different parameters. So we can set, as you can see, x, y, and z, theta x, theta y, and theta z for respectively the position and then the orientation. So let's start with our position. Our position is defined by our T-Cartesian vector. So for us, it's position dot x. Now let's copy this 2 more times for respectively y and z, where we'll send our position y and position z. Then, instead of setting x, let's set theta x, which is defined in our function by the orientation here. So we can take orientation dot x, then copy it twice, for respectively y and z. It's worth mentioning here that the order in which you actually implement this does not matter. You can set z before x and y in any order, and you can also define theta before the actual position values. All that matters is that once you've built your action, all those values are set. And z. Now we want to take a look at our constraint. There are, as I said, two types of constraint. The first one is a duration, and the second one is speed. So if the constraint type is a duration, then you can take your action, set its mutable constraint duration to your constraint duration. And if your constraint is speed, then you have to set two values. You have to set the translation speed and the orientation speed. If the constraint is not set, then we don't need to do anything. Now, in order to execute our action, all we have to do is call the base and execute action. As I said before, since we're calling for an action and there will be a small lapse of time where the robot will actually be busy and we won't be aware of it yet, I'm also adding this sleep function for 500 milliseconds. Our next function is setJointAngles here. We're taking as an input a vector of floats, naming all the angles for each of the joints we want to have, as well as a joint trajectory constraint in case we want to add constraints, either again as durations or velocities to our motion. Like previously, we first check if the robot is connected and if it's busy, and return false if the robot is not available. But we have an additional check here. We have to check if the number of angles is exactly equal to the number of degree of freedom of the robot. This is because if you were to send a command to the robot with too many or too few angles, then it wouldn't know what to do with the leftovers or with the missing values. Now let's define the read joint angle action. First, as before, we can take our action mutable handle, and let's set its action type, set the action type to a Kinova API base read joint angles type. Now, what we want to do is to get the constraints joint angles. Constraint joint angles. So this is a list of joint angles that we will want to set. So this is our constraints joint. This comes from our action mutable reach joint angles. So if you didn't understand yet, the mutable keyword here indicates that we're returning a pointer to a structure. So now we're getting a pointer to a list of joint angles. So now, since this is a list, we need to be able to access all the joint angles in them. So first, Kinova API base joint angles, pointers. Those are from our constraint joint, mutable joint angles. Just in case this wasn't empty, let's take our joint angles and clear them. Now we want to fill in all the joint angles with their constraints. So we will need a loop, for a loop. Let's do int a equals 0, while a is smaller than the number of degree freedom. and increment A. So let's get a pointer to a joint angle. So this is a pointer to a single joint angle and not a list. So to do this, we take our now empty list, joint angle. We take our now empty list, joint angles, and we add joint angles. This new angle, we can set its identifier, which corresponds to the joint we are interested in adding this value to. Set joint identifier to A, and then we can set the value to the values from our vector at position A. So this is angles, this is the STD vector we've taken as a parameter. So this loop will fill in all the angles that were set inside of our values inside this joint angles structure. Now all that's missing is all the constraints that are associated with these joint angles. So if we pass the constraint in our method here, we can look at the type. If the type is not unspecified, then the type can be set for the constraint associated with our joint angles to the same type, and the value can be set as well. This will be valid for both duration and speed. Finally, our entire action is finally set up. We can call execute action and wait while we wait for the base to tell us whether or not we're busy. Now let's move on to twist commands. So our send twist commands method has two parameters, two t Cartesian vectors. The first one, translation, here contains the linear velocity, while the rotation here contains the angular velocity. As usual, we cannot send the command to our robot if it's not connected. However, it's worth noting that twist commands have priority over regular actions. This means that if you already have a regular action running and you send a twist command, the twist command will interrupt the regular action in order to proceed. This is one of the causes of the action abort callback that we can catch here. If we wanted to, in our program, to avoid this kind of priority, we can still implement this here to check if the robot is connected or is busy. But for now, let's say that we're not interested. And if we have an interruption, then it means it's an error. So we want the robot to keep busy until we actually fix our program. So first we check if the robot is available. Then we need to build our twist command. So our twist command is from the Kinova API base, and we're only making a twist command that we'll call command. Our command has a mutable twist that we can edit each value individually. As you can see, we can edit the linear values for x, y, and z, as well as the angular velocity values for x, y, and z. So let's start with linear x, and we can take it for translation.x. Then we can copy this twice for y and z. Z, y, y, and z. Finally, once more, except instead of setting linear x, we're going to set angular x to rotation, to rotation x. which we can copy 2 more times for y and z again. Z, y. Then we can send our command using twist command, and that's it. But what if we want to change the Cartesian reference frame where we use those twist commands from? Then we can call our setTwist reference frame here with a Cartesian reference frame as a parameter. Of course, if the robot is not connected, then this will not work. But then what you have to do is to build a frame request and set its reference frame to the frame you're looking for. Then you can call this new client here that we added to the constructor earlier, the control config client, and use set Cartesian reference frame for your frame request. The frame requests that are available are the following: Kinova API common Cartesian reference frame, so you have access to a Cartesian reference frame on the tool of the robot, the base of the robot. The mixed one means that the translation is relative to the base, but the rotation is relative to the tool. And it can also be unspecified. If you don't specify it, however, there will be errors in your code. So whenever you want to use this, you set your reference frame, you send it, and then for as long as you don't switch it again, whenever you send a twist command, then the robot will be moving in the reference frame you chose. Now we can continue to set joint speeds. In the same way that twist commands interrupt regular actions, set joint speeds does the same. So it has priority over regular actions. Also, since this is a joint type command, you also need to make sure that the command you're sending has the appropriate dimension, namely as a dimension equal to the number of degree of freedom. Now we need to assemble our joint speed object. So first, let's create an empty one. So Kinova API base joint speeds, and we can loop through it. So let's use a as an index while it's smaller than the number of degree of freedom. We can increment a. So inside our joint speeds, which is a list of joint speed, we need to access individual speeds. So first, API base joint speed singular, a pointer speed singular. This is equal to speeds from our list, which is empty, and we can add joint speeds the same way we did earlier to add joint angles. Now for this speed we can set the joint identifier. This is associated with the joint index for which you want to set the speed to. And finally you can set the value in degrees per second. Set the value. So we've taken joint speeds as a vector of floats. So let's take joint speeds of A. And now we can send our command using the send joint speeds command and send our entire list. Now let's move on to a few functions that are directly from our client that will be useful outside of our class. So first, let's go with play sequence. So play sequence is simply, you get to execute the sequence from a handle simply by using the base client and calling play sequence from your sequence handle. And that's it. Then to execute actions, we can also use the base client pointer and call execute action from our action. And that's it as well. Let's move over wait while robot is moving for now and also do stop. So the stop function, as I explained in the previous video, is actually a twist command which has priority over regular actions. It's a null twist command. So if you were to implement your own stop function, you could simply send a twist command with zeros everywhere. But since the base already implements this, you can only call base stop. And if the robot is connected, you return true and everything will work fine. Okay, so now we're ready to move back to our wait while robot is moving method. It doesn't look like it because how hard can it be? You have to literally do nothing while your robot is moving. But if this function is not implemented properly, you can get a lot of problems with your program. You will try and send different actions to your robot and it will not know. It will always return false because it will always tell you that it's busy. So in order to avoid this, you need to sleep and wait while you're done. Except just in case you do not receive the signal indicating that your action is done, you want to add a timeout. There are multiple ways to implement timeouts, but the version I will do here is the simplest I could think of. You can make something as fancy as you want in your own implementation. So for my timeout, I will add a variable named cycle and initialize it to 0. So now, while the robot is busy, and while my number of cycles is smaller than my maximum number of cycles set by my timeout, what I want to do is increment my number of cycle and sleep. So this here sleep for chrono. Let's say we sleep for 10 milliseconds. So what happens here is whenever you launch an action, the robot will tell you that it will turn busy as soon as you get the action start. Then if you call wait while your robot is moving, it will come here and loop and do nothing inside this loop, either until your robot is not busy anymore or until you hit the maximum number of cycles. Once it's done, if your number of cycles is too high, it's higher than your timeout, then it means that you never received the callback saying that your robot is not busy anymore, so you have to return false. Otherwise, your robot is done moving, so you can return true. Finally, we're done with our implementation and we can move to our example. So as I said earlier, we moved the initialization function to the constructor so we can remove this. So we still need to know whether or not we're connected. So we will use instead robot is connected to see if we're connected. Now this is a block of code we already had earlier. Same goes for the end. And now it's time to actually do stuff. So let's do our example here. Okay, first let's go to home. So we can imitate what we did in our eye-level movement example. So we can do action type. So this is Kinova API requested action type. And we can set its action type to a Kinova API base reads joint angles. If you remember, since we're going home, the original home action is a set of reach joint angles. So now all we have to do is say robot dot execute existing action. The name we're looking for is home, and the type we want is action type. Now we can wait while the robot is moving, let's say 10,000 cycles. Then let's make an example for Cartesian actions. So we can make a constraint Cartesian action this time. So let's start with creating our constraint. Kinova API base Cartesian trajectory constraint. Let's call it our constraint. And we can use the default constructor. Cartesian trajectory constraint default constructor. There it is. Okay, so now this constraint, let's say it's a speed constraint. So let's get the mutable speed and set its translation value to 0.25 meters per second. And then the mutable speed orientation to 30 degrees per second. Now we were coming from the home position. Now let's ask our robot to move to. Now we need to send a pose defined by two t Cartesian vectors. So first, Cartesian vector. With our constructor, I can send directly the coordinates. So let's use arbitrary values like not 35, 0, not 15. Then another t Cartesian vector. Let's say 179, 0, 0. And finally, we can add our constraint. Then we can wait while the robot is moving for another 10,000 cycles. Then we can continue our example with an angular action. So let's define our pose as a vector of float, std vector floats. This is a vector of joint positions. Again, let's take arbitrary numbers that I know won't break my office. Those values are all in degrees. Let's take 205, 240, 345, and 320. And finally, 180. Note that I've made sure that there are exactly 7 values here in my joint positions because the robots I will be using has 7 degrees of freedom. Now I can use robot dot set joint angles of my joint positions and send an empty constraint, considering I might not care about the constraint for the motion. Joint trajectory constraint. Finally, I can wait while the robot is moving for another 10,000 cycles. You can already tell just by looking at this implementation here that this way we're implementing all of our methods in a class that takes methods here is a lot more convenient when the time comes to write down your scripts, because otherwise your entire block of code would have to contain all these methods and all these definitions that take a lot of space and are hard to follow in a code. Then let's move on to twist commands. So as an example, let's set the reference frame to something else. Let's set the twist reference frame to common Cartesian reference frame. Let's use the Cartesian reference frame tool. Now we can send a twist command. So we need a t-Cartesian vector for the linear velocity. Let's send 0, 0, and 10 centimeters per second downwards in the reference frame of the tool. And let's just not move in the orientation. Zero, 0, and 0. Now, since twist commands are not actions, we do not have access to the isBusy callback. So we will need to sleep manually instead of wait while the robot is moving. This is the one downside of using twist commands. So let's do this std, this thread, sleep for std chrono milliseconds, 10 milliseconds. And let's not do 10, otherwise we won't see anything. So let's say for 2 whole seconds. So this way our robot will move in the negative z axis of the tool reference frame by 10 centimeters per second for 2 seconds. Then we can call robot.stop. Finally, let's make our example for join speeds. So we can make an std vector of floats again. Let's initialize it to a length of 6 with values of 0. But if you remember, I've said earlier that my robot has actually 7 actuators, so I will want the last actuator to be moving. So I will do speeds, push back, and I will add a velocity command just for my last actuator of 40 degrees per second. So robot set join speeds of speeds. Let's do this again for 2 seconds. Oh, I'm missing a capital S here. And then after 2 seconds, the robot will stop. So that should cover all the functions we built today. Okay, so I've just built the program off screen. Let's take a look at our robot and run the program to see how it behaves. So first we're moving home here. Then we're moving to this arbitrary position. Then to another set of joint positions. Then we will move in the reference frame of the tool for 2 seconds in the negative z direction, and finally for 2 seconds we're rotating the last axis. And that's it for today's demonstration. Thank you for joining this hands-on session. I hope you enjoyed it. Stay on the lookout for our next videos on how to use the KORTEX API with asynchronous calls. Have a good day and thank you for watching.